I was learning at school about the water cycle, and our teacher decided at the end of that lesson to tell us about acid rain. So that was my first exposure to anything to do with climate change. And to 10-year-old me, acid rain was a pretty scary idea. I had some sort of vague idea about what acid was. Specifically, I knew it was a colorless liquid, and I knew that it melted things. And so I worried that if I went out in acid rain, perhaps it would melt me, and that didn't sound very good. And how would you know? Because it's a colorless liquid, so presumably it looks a great deal like rain. Well, as it turns out, acid rain doesn't melt people, though it does melt structures and sculptures and those sorts of things. And it also does terrible damage to ecosystems. It strips forests of their leaves, it leaches nutrients out of soils, it pollutes rivers and lakes. It's caused by a gas, sulfur dioxide, which is a gas that we emit when we burn coal. And because it's a gas, it pays no attention whatsoever to international borders. Emissions from here in the UK would blow across to Europe and typically fall in the Nordic countries as acid rain there. Emissions from the US would blow across to Canada and fall as acid rain there. And those emissions were serious enough that they used to cause major diplomatic incidents. So you might be wondering why you haven't heard about acid rain in a while, and the answer to that question is because we fixed it. So we signed these seemingly rather clunky international agreements, and those international agreements turned out to be incredibly effective. In Europe, sulfur dioxide emissions fell by about 90%, in the US by about 95%, here in the UK by about 98%. So we don't talk about acid rain anymore because it's no longer a problem for us. We solved it. We did something similar with the ozone hole. So we signed the Montreal Agreement in 1987, and after we did that, emissions of hydrofluorocarbons and the other ozone-depleting substances basically dwindled away to nothing. Now, that doesn't mean that the ozone hole is closed. That's something that will take a very, very long time. But what it does mean is we're not making the problem any worse. And I like to start there because I think when you start thinking about climate change and your role within it, it's very easy to get stuck in a kind of doom loop, where you start thinking, gosh, this sounds terrible, but there's nothing very much I can do about it, and with a bit of luck I'll be dead or too drunk to notice or something like that. Or perhaps I'll go and throw some soup at a picture by Van Gogh. I'm not quite sure why, but maybe that will help. It won't. What will help is doing proper engineering, and what's interesting to me is that having got very depressed about climate change and decided I'd go and do something different with my life, coming back to the field has been kind of exhilarating because I've realized that actually things aren't nearly as bad as I thought they were. They are still quite bad, but we've made real progress. Unfortunately, we're not quite out of the woods yet. So the next problem we have are the greenhouse gases. These are a family of gases. It's things like methane, nitrous oxide, carbon dioxide. And what they do is they sit in the atmosphere and they trap heat. It's to do with wavelengths of light. But basically, light from the sun can pass through them one way, bounces off the Earth, can't pass back through them. Okay? They are something of a mixed blessing. We really need greenhouse gases. If we didn't, the average temperature on planet Earth would be around about minus 20 degrees centigrade. That's pretty chilly, and also, as it turns out, too cold to sustain most life. So we really do need them. The problem that we have is since the Industrial Revolution, 1850, we've been burning a lot of fossil fuels, and a side effect of that is we've been increasing the concentration of greenhouse gases in the atmosphere. And what that's led to is we are gradually warming the planet. That's what this graph, this is the famous Bradley Manning hockey stick graph, that's what it shows you. Now this is a temperature anomaly graph. The blue shaded area there is the margin for error. It starts in 1000, so as you would expect, the margin for error is quite wide there, and it narrows as we get closer to the present day. Basically, it bundles along doing nothing very exciting until 1850, and suddenly it climbs really sharply. Now, I don't know how easy it is for you to see the vertical left-hand axis there, but it's minus 0.8 to plus 0.6. So what you're looking at there is half a degree centigrade of warming, which, doesn't sound that bad, and actually isn't, really. I'm sure you know that the sort of scientific consensus is we want to keep our warming at 1.5 degrees. That's to say 1.5 degrees centigrade above pre-industrial levels by 2100. And you probably also know that that's not going to happen. In fact, last year we had multiple days where we were above that average temperature. That doesn't mean the goal is gone, because the goal is averaged over decades. But it is it is a sign that we are kind of at that threshold. In fact, most of the predictions that I've looked at come out about 2.7 to 3.5 degrees centigrade of warming, and that's not great. However, when I decided to go and do something else with my life, we were looking at 6 or 7 degrees of warming. So actually, 2.7 to 3.5 represents real progress. My point is, there's a lot to do still, but we are actually making progress. I am not a climate doomer. I firmly believe that climate change is something that we can solve, and I firmly believe that we as a species will survive this, if we want to. We have to want to. But we're at a tech conference, so what does any of that have to do with technology? And the answer to that is, we emit one of those greenhouse gases in quite large quantities. The specific one is carbon dioxide. We emit some of it with our hardware when we manufacture stuff, transport stuff, dispose of stuff. We also emit a great deal of it when we run our hardware. Now, something that was a surprise to me was that until quite recently, emissions from our data centers weren't actually rising very much. As we shifted to public cloud, we basically consolidated on this utility computing model. We ended up with a relatively small number of providers. Here in the West, it's really 3 big ones. They are very good at running data centers, so the data centers got more efficient. At the same time, our servers got more efficient. And the net result of that was, even though we were adding large quantities of compute, we weren't increasing our emissions very much. Nevertheless, according to the IEA, the International Energy Agency, our emissions for 2022 were somewhere between 240 to 340 terawatt hours. That's about 1.3% of all global electricity demand. That figure does not include data transmission networks. And a data center you can't get stuff in and out of is fairly useless. If you add data transmission networks in, you double that number, actually slightly more than double. It's about another 260 to 360 terawatt hours. So we're now up to somewhere between 2 and 3% of all global electricity demand. For perspective, that's about the same as a country like Brazil, or if you prefer, it's about as much as the aviation industry emits in a year. Just for fun, by the way, crypto mining is the same as Norway on its own. So if you want a really pointless endeavor, there is one. The good news, so with the acid rain example, there was something that I neglected to tell you. So I said we signed these international agreements, and these international agreements were incredibly effective. What I didn't mention was that the other part of that was the cost of sulfur scrubbers. So sulfur scrubbers are the things you put in power station chimneys that do what it sounds like. They take the sulfur away, or the sulfur dioxide away. And the cost of those started to fall quite rapidly. They are still expensive, but what that meant was that countries felt kind of compelled to act because they'd signed international agreements that said that they would, but they also felt able to act because acting wasn't going to cripple them financially. The good news for us is that the cost of low carbon computing has fallen quite dramatically. So in the case of solar energy, that's fallen by more than 90%. Price of wind energy has fallen by more than 70%. Battery costs have also tumbled. That's all in the last decade. And that technology has started to get a great deal better. And what that means for us as an industry is that actually shifting to renewables is generally cheaper, though it's not absolutely guaranteed, and we'll talk about why that is as we go. Now, in my day job, I do a lot of consulting work, and when I go and talk to clients, my favorite tool is something called a maturity matrix. They are a bit of an oversimplification, but they're great, because what you can do is you can sit down with a client and you can say, draw out where you think you are, and then we'll work out where you want to be, and then we'll figure out how to get from one to the other. So typically, what you're trying to do basically is move from left to right. This particular maturity matrix is one from the Green Software Foundation. They do a lot of good work in this space. They're an offshoot of the Linux Foundation. It's in GitHub, so you can go and grab it, and I encourage you to do that and fill it in for your own companies. If you do, you'll probably find, with a bit of luck, you're somewhere over here on the left-hand side in what we call aspiring. I will say some of my clients and prospects, I'm not sure have even made it to aspiring yet, but I live in hope. If you are on the left-hand side of the maturity matrix, that's actually quite good news. We all have to start somewhere. And the wonderful thing about being on the left-hand side is a lot of the things that you can do are actually quite simple. And they make a huge difference, which is good news. as you get further to the right, this stuff gets harder. So a lot of this talk is going to be talking about basically how you move across this board. But before we do that, I'm just going to do a quick terminology level set. So over there, we've got these scopes 1, 2, and 3 carbon. These come from something called the Greenhouse Gas Protocol, which is the most sort of widely recognized way of reporting your carbon emissions. So if you've ever seen a carbon emission report from a company or had to do one yourself, this is what you use. Your scope 1 emissions, those are the things that you are directly responsible for. So that's things like fuel combustion on your own sites. If you have data centers with diesel backup generators, the diesel backup generators would be scope 1. Scope 2 is stuff that you buy in that you need directly for your operation. So that would include your electricity, because you don't make that yourself, you buy it from the grid like everybody else. It would also include heat and those sorts of things. If you need detail on exactly what's in Scope 2, the 2015 version of the Greenhouse Gas Protocol goes into that in enormous and somewhat tedious detail. So that's the one to refer to if you need to be absolutely sure. And then Scope 3 emissions, those are the emissions that are the rest of your supply chain. So the Scope 3 emissions in most companies are going to be by far and away the largest thing. It's also typically the hardest thing to report on and actually get data on. The other thing in here, those scopes can be a bit difficult to map to what we do in IT, and it's probably worth saying that there is kind of a perspective on this. So your perspective would be different from your cloud provider's perspective if you're running stuff on cloud. But for you, your private cloud stuff, your energy consumption, so your electricity is going to be scope 2. Your embodied carbon, so that's the carbon that's used to manufacture, transport, and ultimately dispose of the hardware you use, that's all scope 3. If you're running everything on public cloud, everything is scope 3. If you're using a mixture, well, some energy is going to be scope 2, because some of that's in your own data centers, and everything else is scope 3. And finally, the front-end stuff is all going to be scope 3, because obviously that's running not on your hardware, but on someone else's hardware. The other thing in here that I wanted to just make sure we're all familiar with is this idea of carbon neutral and carbon zero and offsetting, because again, this is terms that gets thrown around quite a lot, and I think definitions here can be helpful. So to be carbon neutral, an organization has to measure its scope 1 and 2 emissions and then match the total with offsets through carbon reduction processes. So what that means, first of all, is you can be carbon neutral with no idea about your scope 3 whatsoever. That is allowed. Most businesses do include business travel, which is scope 3. And they offset that. The other thing, of course, is offsetting is allowed. So essentially what most companies do here is they buy a load of carbon credits and they say, there we are, we're carbon neutral now. A lot of people in green circles will tell you that carbon offsetting is kind of a waste of time, and they sort of have a point. But I think this is a pretty reasonable first step, particularly if you're actually paying for it in some way, because I think it's quite helpful if your carbon emissions start affecting your bottom line in some way. I would love us to have a carbon tax, but we don't, at least not yet. So in the meantime, I think this is a reasonable start, but it doesn't get us where we need to go. Where we need to go is net zero, and net zero is reducing emissions according to the latest climate science, and then removing the residue emissions through carbon removal. That's removal, not offsetting. In reality, we don't have anything like sulfur scrubbers for carbon. There are things in labs, there are experiments, there are possible ways of doing carbon removal, but none of them seem to scale so far. My honest opinion is we probably don't have time to wait for that answer. So my honest opinion is we need to be finding ways of getting to carbon-3 that don't rely on us being able to remove the carbon later on through some mechanism. I don't think we're going to get there in time if we try that. Fine, so that's carbon neutral, net zero, offsetting, great. Over on the right-hand side of the matrix, we have this inspiring column. So what does inspiring mean? Well, it means 24/7 carbon-free electricity in your data centers. There is a weird accounting trick you can do where you can buy what's called unbundled RECs, at least in the US. What that means is you run your data center in Virginia, you buy a load of green energy somewhere else, and you say, look, I'm carbon neutral in Virginia. It's allowed under the Greenhouse Gas Protocol. It's a bit peculiar. Google is, as far as I know so far, the only cloud provider who has committed to getting to 100% renewable data in their data centers by 2030. I'm not convinced that they'll get there, but I admire them for at least giving it a serious go. But that's what we want to do, right? We want to get to a point where we're using carbon-free electricity. I should say, by the way, carbon-free electricity does include nuclear. Nuclear is a carbon-free energy source. And we do need nuclear to be part of the energy mix for the foreseeable future. I don't have time to go into why I said that, but feel free to ask me afterwards if you're curious. The other thing in here is 10-year life expectancy on all end-user devices. So our laptops, our mobile phones, those sorts of things should last 10 years. We're quite a small room here, and I'm struggling to see you under the lights, but hands up if anyone has a 10-year-old laptop or a mobile phone. Anybody? Somebody does. Ace. There's usually one person. It's fascinating. I'm starting to think it's the same person, and they're following me around. It's always one. Anyway, yeah, in general, we don't, right? In general, we throw our laptops away after 4 or 5 years and our mobile phones after about 2 or 3, as a rule of thumb. We need to get better at this. If you are involved in procurement for your companies, I would encourage you to look for hardware that gets supported for the longest time, and then put pressure on your suppliers to extend the lifetime further. The reason for this business on end-user devices is to do with the embodied carbon. So with a device like a laptop or a mobile phone, the carbon that's used to manufacture it and transport it absolutely dwarfs the carbon that's used to charge it in its lifetime. I've linked there to the iPhone 14 environmental report, just because it's the easiest one to read, but they all come out pretty similar, and it's 84%. Right? So 84% of the carbon in your iPhone is actually in the manufacture of it. Does that make sense? So that's what we want to do, is we want to make less of them, basically, and that's why we want to extend the lifetime of them. With servers, TPUs, GPUs, it's not quite that straightforward, and I can't give you a simple heuristic. You kind of have to run the numbers yourself, because servers, TPUs, CPUs keep getting more efficient. In data centers, a lot of the energy we use is actually in cooling, a huge amount. And so more efficient CPUs make quite a big difference. And because of that, I can't really give you a number. You just have to run the sums yourself and figure it out. Right, good. Okay, so this is a tech conference. We're all developers, right? So at this point, you're thinking, right, I want to make my applications more efficient. So what I'm going to do is I'm going to run a load of benchmarks to figure out what the most efficient languages are. Here's a benchmark that does that for me. And I'm going to look at that and say, right, C, C++, and Rust. Those are the most efficient languages. So I'm going to rewrite everything in C or C++ or Rust. Yes? No. We're not going to do that. Doing that would be probably a fairly silly thing to do. And actually, if you went to your business and said, I want to rewrite everything in C or C++ or Rust, they are very likely to say, well, yeah, we're not doing that. Because, well, there's a reason why we use higher level languages, and it's time to value. In fact, I've been in this industry 30-something years at this point, and I would say that every significant thing that has ever happened in our industry in the time I've been involved in it, has actually been about shortening time to value. That's to say, the time it takes to go from having an idea to getting that idea in front of your customers and verifying it. I would argue that that explains higher level languages, whether those are Java or C# or, goodness me, Visual Basic even, perhaps. I would say that it explains Agile. I would say it explains DevOps, team topologies, fast flow, all of those things. They are all about trying to get ideas in front of customers more quickly. So if you go to your business and say, we're going to write everything in C and C++ and Rust, they are going to go, no, we're not doing that, because it's going to take too long. But the other thing is, well, here's Java on this particular benchmark. Okay, it's not as quick as C, but it's not bad. The JVM itself is a fantastic piece of technology, and a lot of very good engineers have spent a staggering amount of time making it more efficient in various different ways. And what that means is you're much better off focusing on the versions of the runtimes you're running in production, because each version of the runtime will get better. So for Java, what that means is you want to be on, at the very least, the most recent long-term supported versions, if you possibly can be. Framework choice does also make a difference. It depends a bit on your scale, but if you're running apps, a large number of applications, then framework choice does make a difference. The Quarkus team did a huge amount of work on Quarkus to make it more efficient. They didn't actually do that for carbon reasons, by the way. They did it because they needed faster instantiation for microservices. But it turned out that stripping out reflection and all the other things you might do to make Java faster also made it much more carbon efficient, which is good. So framework choice makes a difference, but the main thing is be on the latest versions of the runtimes. Even dear old Python, which languishes down the bottom of this particular benchmark, is getting better. I mean, it's still Python, there are limits, right? But it's improving, but you only get those benefits if you're using the latest runtime. So the very first thing to do is to start by thinking about, well, what versions of the runtimes am I running in production? Can I move to the later versions? That makes sense from a business reason, but there is also a technical reason. And the technical reason is something called energy proportionality, which is a fine example of how naming things is hard. It's a terrible name. It should be called energy disproportionality, if we're going to go with that. But anyway, it comes from a paper from Google. And basically what Google realized was that when you turn a server on, it has a static power draw. And that static power draw is quite a lot. And then as you start putting work through it, it doesn't follow a linear progression in any meaningful way. So the upshot of that was, basically the optimum window at the time this paper was done was about 50 to 80%. Okay, so below about 50%, the server is using less electricity than it needs to do the workload. Above about 80%, you start getting contention on the CPU and queuing contention, those sorts of things. Not good. So we want to be in that 50 to 80% window. Less efficient servers, that window will be slightly different. Very modern servers may look slightly different again. Again, you would need to benchmark this to know exactly where it comes out for your particular workload. But aiming at about 50% or above is a really good starting point. So if you're running stuff in your own data centers still, aim for greater than 50% utilization of CPUs across your entire estate. About 18 months ago, I was talking to a prospect in a large meeting of very senior C-suite people, and I said that, and they looked at me and went, which is never a good sign. They were like, that sounds really hard, Charles. And I was like, well, yeah, it does, doesn't it? Because it is. And part of the reason it is actually a weird historical accident. When I started in this industry, which was, goodness me, 30-something years ago, procurement was unbelievably slow. And also we didn't have multi-tenancy, which meant that when we installed a new app into production, we had to buy servers specifically for that app. So the way this would work is someone from procurement would come to me and they would say, this new app of yours, how many servers do you need? And what I would do is I'd work out the maximum possible number of simultaneous users that I would ever expect to see on the app. I'd build a database of about that size. I'd write a load of load tests to simulate that load. I'd figure out how many servers that was. And suppose that was 4 servers. I'd go to procurement and go, 8, please? Right? And no one ever said, why do you need 8? Because we understood that over-procurement as a risk management strategy was just a thing that we did. And the reason was because if I needed another server, well, that was a process that literally took months. I'd have to sign a form, and then 10 other people would have to sign it, possibly in blood or something. And then that would go and sit on somebody's desk for a month, and eventually a piece of hardware would get bought, and then that would sit on somebody else's desk for a month, and then they'd eventually put some software on it, and eventually put it on a rack, and eventually we were talking months and months and months. Now we're on public cloud, of course, we don't have any of those problems, right? We have elastic compute. That was the point, but we still over-provision everything anyway, because we've always done it that way, so why would we change? So, yeah, as I say, aim for higher utilization. That's a very good thing. The other problem with over-provisioning is something called a zombie server. So a zombie server is a server that was once doing useful work, but no longer is. They're desperately easy to spot. That's what they look like. If only that were true. My thanks to my friend Mickey for drawing that. I couldn't have done it myself. Anyway, yeah, so zombies are bad. You know this, right? You've all seen zombie films. We want to kill our zombie servers. How bad are they? Well, in the Building Green software book, that's the Ann Curry, Sarah Bowman, Sarah Sue book from O'Reilly, they have a story from Martin Lippert, who is Spring Tools lead at VMware Broadcom. And he says that in 2019, VMware consolidated a data center in Singapore. The team wanted to move the entire data center and therefore investigated what exactly needed a migration. The result was somewhat shocking. 66% of all the machines in their data centers were zombies. I've run audits for a couple of companies, and I will tell you that's not unusual. In my experience, roughly half of all the servers in every data center I've ever been into are doing nothing helpful. That's not great for your bottom line, by the way, because you're paying for those servers. It's also obviously very bad for the environment, and it's also terrible for your security posture, because what tends to happen with servers that are zombie servers is we don't monitor them as closely, and people don't complain when they break, and we don't update things. And the result of that is they are vulnerable to attacks. In fact, there's a quote from Ed Harrison here, who's former head of security at Metaswitch Networks, now owned by Microsoft. Some of the biggest security instances in recent times have stemmed from systems which no one knew about and should never have been turned on. So zombies, bad for your bottom line, bad for your carbon footprint, bad for your security posture. The trouble is they don't look like my nice picture. They're actually quite hard to spot. There is a recognized way of doing it. It's called a scream test. What you do is you turn the server off and you wait to see if anybody screams. Last year, I met someone at a conference in Copenhagen who worked for a bank. I can't name the bank, but they'd actually automated this. So they had an eco-chaos monkey that would sit there and monitor the servers. And if the server didn't do anything for a week, they'd turn it off and see if anybody noticed. So I thought it was genius. In a lot of companies, turning off servers does make people quite nervous. And the reason for that is because we worry about our servers and their idempotency. We worry that if we turn them off, they might not be quite the same when we turn them back on again. And I suspect all of you in this room, if you've been in this industry a little while, have had that experience, right? You've shut a server off, you've turned it back on, it turns out there's some firing dependency order thing, and it doesn't work anymore, and you've no idea why. This is beautifully encapsulated by Holly Cunnings. She calls it light switch ops. That's where it appears in the maturity matrix. And her idea basically is we want to get to a point where we can turn our servers on and off as easily as turning a light switch on or off. So she talks about this idea that at the end of the day, when you leave the office, you switch the lights off, you switch your Kubernetes clusters off, right? It's a nice idea. You could start doing that with your test and development servers, right? Switch those off in the evenings at weekends when you're not using them. That will make a difference on its own, but it will also get you into the habit of working out how to make your servers turn on and off reliably, and then you can start doing that stuff in production. If your business isn't global, you will have hours of peak demand and hours of less demand. You could think about scaling your servers up and down accordingly. That would be a good thing to do. Typically, with all of this stuff, which is basically manual right-sizing, we tend to only do it when we're moving data centers. So what I would encourage you to do is take a chunk of time, a quarter maybe, or even maybe just a sprint, and run an audit. Find out what your servers are doing, get rid of anything you don't need. If you know you can bring it back up again easily, then you can afford to be brutal. So that's manual right-sizing. Of course, we do also have auto-scaling options. So if you're running in Kubernetes, Kubernetes has auto-scaling built in. If you're running some stuff on public cloud, all the public cloud providers have ways of doing auto-scaling. I have discovered an interesting thing, which is people tend to auto-scale up and not down again. You are missing the point. If you are doing that, please auto-scale down again. Otherwise, why are we even bothering? If you do have stuff in your own data centers, you have some advantages over people running solely in public cloud. Not many, but some. In general, running in public cloud is going to be more efficient, right? But if you have to run in data centers, there are some things. One of those things is you have control over the lifetime of your hardware, right? So I mentioned earlier about the embodied carbon. If you're running in your own data centers, you get to do those sums and figure out exactly the optimal time for getting rid of old hardware and replacing it with new hardware. You can't do that in public cloud. Someone else is managing that for you. You can also take advantage of the power-saving features that are enabled on all of your servers. No, they're not. They are available on all of your servers. They probably are not enabled. Enable them. That makes a massive difference. So basically all that does is it sort of puts the server to sleep when it's not working. We have a nervousness about this. It's the same nervousness we have about light switch ops. I have had servers that don't come back when they've gone to sleep for reasons that are not always immediately obvious, but they can be debugged. Doing that, again, makes a massive difference, right? Because if you've got an awful lot of overcapacity in your data centers, then having things that are running at lower speeds is going to make a huge difference. CPU choice is another of these things that I think most of us don't really think about very much. Probably it may be a reflection of my age, but because of when I started in the industry, I tend to think Intel first, at least in data centers. And historically, that was a perfectly reasonable thing to do. And if you like provision in cloud, I imagine Intel is probably the default on most public clouds. Intel, of course, lost mobile ages ago to ARM. Intel lost data centers ages ago to AMD, and the reason for that is because AMD has better core density. So typically, for most workloads, you'll get about a 29–30% efficiency, somewhere around that, 29–30% efficiency gain by switching your workload from Intel to AMD, as a rule of thumb. Now, do check those numbers for your particular workloads. There are places where Intel will win, and obviously these things change over time. So if you're watching this back on the video later, check those numbers. But in general, you'll get more cores, which means you can do more things, in theory, on an individual server. I've actually run some of those numbers for my ebook, which is a free download, so if you want to get more on that, you can. ARM might be more efficient still. That's slightly more complicated in data center than it is in mobile, but it's absolutely worth thinking about. With ARM, you normally have less cooling to do. It's why we like it in mobile so much, and as I said, cooling is a factor. The other thing is your hardware has a voltage range. So every server you own will have a range of volts that it supports. So think about, can I send that server the lowest supported voltage? If you're operating at scale, that makes a huge difference. If all of this is starting to feel a bit too hardware and you're a software person, that's fine. Hopefully you have hardware people. Go and talk to them and get them involved. They'll have more ideas than I do. But voltage range is another good one to think about. There is an adage in our industry that we can't fix things we can't measure, and that's a great shame for carbon computing because measuring is still really difficult. A lot of the time, we have to rely on proxies. CPU utilization, as I mentioned, is a really good proxy to use. Another good proxy is cost. If you are at the left-hand side of the maturity matrix, if you are bringing your costs down, you are also, chances are, bringing your carbon emissions down. Right? There's a point where that ceases to be true because the cost of green energy isn't cheaper, at least in the UK. It varies. Some countries have differential pricing for different sorts of energy. In the UK, we don't, at least not yet. This is actually an interesting point. So in Bill Gates' excellent book, How to Avoid a Climate Disaster, he talks about something called green premiums. And the green premiums are basically the cost for a business of going green, right? He doesn't calculate one for IT, perhaps surprisingly. I am going to say to you, I reckon it's a negative number. That's to say, I think for us as an industry, going green is actually going to save us quite a noticeable amount of money. You know, of order of 50% or so. Right, so what I'm saying to you is you can probably halve your IT bill without getting rid of anybody just by getting rid of redundant stuff. It does get a bit harder as we go further along. The CNCF has a project called Kepler. I've only recently started playing with Kepler, and I'm kind of blown away by how good it is. It uses eBPF to get a whole load of energy-related stats out of Kubernetes, and it exports them as Prometheus metrics. They also have a pre-built Grafana dashboard, so you can drop those straight into Grafana and get really quite a good idea of what's going on for your Kubernetes workloads wherever they are running. So this is a really great tool. Obviously, it's open source, it's free. If you're running stuff on public cloud, the cloud providers all have carbon footprint tools of, shall we say, varying levels of usefulness. So AWS has the customer carbon footprint tool, Azure has the emissions impact dashboard, Google Cloud has carbon footprint. I'm going to risk saying this on camera. I wouldn't normally say this on camera, but hey, it's a Thursday afternoon, so what the heck. The Google Cloud footprint tool is actually really pretty good. It is the best of the three, I would argue, by quite a long way. The Microsoft one is quite usable for you as engineers. You can do useful stuff with it. The AWS one is not in any way useful for you as engineers, not even slightly. The only thing you can use the AWS one for at this point in time is getting your CFO to buy carbon credits, and that's what it's designed to do. It's absolutely useless for optimizing workloads. Now, slightly in AWS's defense, they have, as of about, as far as I know, 6 months or so ago, put a new team together to work on a new version of the customer carbon footprint tool. There are signs of life. Hopefully it will get better. But if you are in the extraordinarily luxurious possession of picking a cloud provider and you want to optimize for carbon, don't pick AWS, at least not today. Cloud Carbon Footprint Tool is an open source alternative that's sponsored by ThoughtWorks. You can use that across different clouds up to a point. The data that the different cloud providers provide is not yet in any way comparable, so you can't really say, oh, look, I'm doing more on Microsoft than Google, because the numbers aren't really comparable in that way. There is an initiative being run by Adrian Cockcroft, who used to be head of sustainability at AWS, is now kind of retired. But he's working on an initiative to try and get standard data from all the cloud providers, which would mean we would finally be in a position to actually compare what they're doing. It's a very ambitious goal. I think it's a really cool project. It's not quite ready for prime time, but keep an eye on that one. The GSF has a formula. The formula is quite good for working out your workloads. It's less good for doing actual carbon reporting. But if you're trying to figure out what is this workload doing, the GSF formula is great. I'm not going to try and explain it. I've linked to a blog post there that explains it far better than I would in the time that I have available. But I will mention one thing about it, which is that it has a location element. Location makes a huge difference to the greenness of your workloads, because moving to carbon-free energy is a transition, which means that we're not all getting there at the same time, right? So different countries have different mixes. Also, the actual time of day makes a huge difference, because on our grids, we don't have a lot of buffering, we don't have a lot of storage, which essentially means that we can't make weather yet, anyway. So what that means basically is you get more carbon-free energy if the sun is shining and you're in California at 12 o'clock than you do at, say, 6 o'clock in the evening. One thing that means is that you can literally just pick where your workloads go. So if you have a choice of data centers and you're running on public cloud, use a tool like electricity maps to go and figure out where the workloads are greenest, and literally just stick your workloads there, and that makes a huge difference. Working this out, by the way, is actually really hard. Working out whether energy is green or not is really tricky, but electricity maps do a really, really good job of that. So that's a really good starting point. This observation has led to something that's called carbon-aware computing, and carbon-aware computing is basically about optimizing your workloads to be as green as possible. I have some reservations about carbon-aware computing. I think it's a useful tool to have in your toolbox, but I think it's very much one of the very last tools you reach for. So do the operational stuff, get your operations right first, and only start reaching for things like demand shifting and shaping when you've exhausted all the other possibilities. But just briefly, so electricity maps, watt time, WATT, and the GSF all have APIs. There are some others of these springing up. What they basically do is they do a prediction of the greenness of energy for the next time window, right? So for the next 3 hours, we reckon we're going to be 100% renewable, for example. So what that means is you can then think about running workloads that are computationally expensive at times when the grid is greenest. You can do that time-based, but you can also do it location-based, at least in theory. So you can have workloads that essentially follow the sun or follow the wind around. That only works if you haven't got a lot of data to move. So if you've got a lot of data to move, I think you're much better thinking time-based than location-based. Somewhere in the last 4 or 5 years, we suddenly decided that microservices were a good idea. I don't quite know why. And so now everything is a distributed system. And what that means is there are a bunch of things that we had to do to make our distributed systems more resilient that also are quite useful and can be applied in a carbon-aware way. A great example of that is graceful degradation. So with graceful degradation, what we do is if we can't reach a service in time, we respond with some stale results from somewhere. That's typically how it's done. So Netflix is a great example of this, right? If the movie recommendation service doesn't respond in time, they'll get some stale movie recommendations from a cache and show you those. And you probably don't notice. And if you do notice, you probably don't care. Why is it showing me that piece of rubbish that I've already watched? But mostly you don't care. There are lots of other places in the homepage on Netflix, by the way, where if it doesn't respond, it just doesn't show you anything. The widget just disappears, and you probably don't notice that either. There are lots of places where we can do that sort of thing. So from a carbon awareness point of view, what we could do is basically do the cache discard at the point at which we're predicting the energy to be greenest, refresh the results, and then serve from the cache until the next time we've got a green window. Making sense? Fantastic. There are real-world examples of this. So Google launched a project to make some cloud workloads more carbon-aware. It says it can shift movable compute tasks between different data centers based on regionally hourly carbon-free energy availability. Microsoft has a project to make Windows 11 more sustainable by running Windows updates when the carbon intensity is lowest. They also have done work with Xbox, so that Xbox, again, will do its updates when the grid is clean, but it will also have low power mode. So we're back to low power modes. And according to Microsoft, that, which they call shutdown, is a 20-fold, a 20 times energy saving, which is kind of interesting. So that's pretty cool. Apple has clean energy charging. I think this is still US only, as far as I am aware, for iPhone. And again, it does the same thing. Basically, it uses a forecast of the emissions and charges your iPhone at the point when the locally available energy is as green as possible. Now, obviously, both Xbox and iPhones and user devices, therefore the embodied carbon is a bigger problem. But nevertheless, I think it's kind of good to see these things happening. At least we're starting to learn how to do this stuff a bit better. Right, I have 10 minutes. This is a conference talk in 2025, so I am, I believe, legally obliged to mention AI. Otherwise, it's not an official conference talk. Mentioning AI in a green context is quite difficult, and one of the reasons it's quite difficult is because although we know AI is very expensive, computationally speaking, the big AI companies don't want us to know that, and so they won't give us the data. What you have to do to find this out is scratch around in their environmental reports and see what you can find there, at least for the companies that publish the environmental reports. Because one of the many things I do is tech journalism, so I spent a whole load of time reading an awful lot of environmental reports to figure out what was going on. And lucky you, you don't have to do that. Microsoft reported in May of 2024 that its total carbon emissions have risen 30% since 2020, primarily due to construction of data centers to meet its push into AI, right? 30% since 2020. Google's emissions, meanwhile, have climbed 50% since 2019 and 13% in the year of 2023 alone. And again, that's down to their push into artificial intelligence. OpenAI doesn't give us the data, so we can't tell. But that's just to give you some idea. If you remember right at the beginning of the talk, I mentioned the fact that our data centers hadn't been increasing emissions for a long time. That's not true anymore. We are increasing emissions at an extremely alarming rate just now because of AI. Specifically Gen AI, by the way, just to be clear, because we talk about AI like it's one thing, and obviously it isn't. Gen AI specifically, large language models are very, very inefficient. They don't have to be. That's a choice we make as an industry, which is interesting. At least it's interesting to me. For a start, training an ML model is not in any way latency sensitive. So you could make a choice to say, I'm going to train my machine learning model on 100% renewable energy. It would take a bit longer, but it's totally doable. Right? Now, the reason that we don't do that is because we have this sort of mythical idea that we're going to be behind the curve and our competitors are going to overtake us, and it's mostly nonsense, and it's also a problem of messaging. Right? If you went out to your customers and said, we think generative AI might turn out to be useful, but we're doing it in a way that we're going to get it right, we're going to do it in an environmentally friendly way, we're not going to tell you to eat rocks and stick glue on your pizzas, I reckon a lot of your customers would probably be pretty good with that. That's my opinion. If we did that, according to research from University College Dublin, then the net result would be a reduction in carbon emissions of between 45 and 99%. So just doing time shifting on its own is pretty dramatic. There are a bunch of other techniques. Federated learning, which is essentially doing machine learning at the edge, is another one that can, in a lot of cases, be really good for this kind of stuff if it's done cleverly. And there are a bunch of other options here. The basic rule of thumb is training is expensive, so if you can use a pre-trained model, don't train one from scratch, fairly obviously. If you are using a pre-trained model, keep in mind that training isn't all of the cost. In fact, it's probably not the most expensive bit. Probably the most expensive bit is inferencing afterwards in production. It's very hard to get real numbers on that at the moment, so I don't know for sure, but I'm going to say it's probably about 60-40. That's to say 40% of the cost is training, 60% is running it afterwards. That doesn't mean the per inference cost is very high. Actually, it's not. But if you do it at scale, it becomes incredibly expensive. Just as an example, so Meta's OP175B, that was their equivalent of GPT-3, was trained with 1/7 of the electricity of GPT-3 and is pretty comparable on most benchmarks. We can't do those comparisons for GPT-4, of course, because OpenAI won't tell us what GPT-4 costs to train. Apple have also said that they get tremendous efficiency out of their own silicon. So their push into generative AI, they say, is not affecting their push to be 100% renewable by 2030. I'm assuming that that's ARM. Again, they haven't said that it is, because it's Apple, so of course they haven't. But given that all of Apple's silicon that we know of is ARM, I'm going to assume that's ARM as well. So I think that's another example of where your CPU choice makes a difference. There are some benchmarks and leaderboards beginning to appear specifically for open source models. So there's something called ml.energy, which is a pretty serious piece of research that's starting to do carbon benchmarks on different machine learning models. Of course, they can only do the open source ones, so that's another way of saying pick open source models if you possibly can. Right, what do we expect to see next? Well, I think we'll see more regulation. We already have ESG. ESG is not brilliant, but it's something. The reason I say it's not brilliant is because it's very easy to game it in a whole variety of different ways, and people do. But it's still something. And a lot of times in Europe, companies actually use ESG as part of the vendor selection criteria. So if you're selling business-to-business software, worrying about your ESG score is quite a good thing. The EU also has something called the Carbon Border Adjustment Mechanism, CBAM. And that basically aims to make all EU suppliers green. It's in a transition period. It will be fully operational by 2026. That's effectively a carbon tax for EU, which is quite interesting. So bringing your costs down, again, is going to start to make a difference. I have a feeling this is going to be one of those things a little bit like GDPR, where initially everyone goes, that's a terrible idea, and then they all copy it later on when they think, actually, maybe it wasn't such a terrible idea. I think carbon tax would be a very good thing, because at the moment, the problem with, well, anything greenhouse gas related really is your company doesn't pay for it. Right? The people who pay for it are the generations later down the line who are standing there with water around their waists wondering if they're going to drown. It's not your company, and that's a shame. What else can you do? Well, your best friends are going to be your head of security, because it's better for your security posture, your CFO, your chief financial officer, because it's cheaper, and maybe also your head of recruitment, because if you are struggling to recruit people into your company, I think, at least engineers, I think being able to say we take sustainability seriously is going to get you really good people. Pretty much all of the best engineers I know work in this space now. You have the opportunity to put pressure on your vendors. So if you're buying a lot of stuff from somebody, it is quite reasonable for you to go to them and say, tell me about your carbon footprint. And if they won't tell you about their carbon footprint, it's perfectly reasonable to find another supplier that does. Adrian Cockcroft, who was head of sustainability at AWS, was quite open about the fact that AWS only has a sustainability initiative because their customers kept telling them that they would go to Google if AWS didn't put its house in order. Right? You have a lot of power if you buy stuff. By the same token, with some caution, I'd also encourage you to talk to the maintainers of the larger open source frameworks that you use. At the very least, ask them if they've thought about sustainability, and if they haven't, ask if you can help. We need to get better at this as an industry, and open source would be a really good place to do this. Obviously, the reason I say with some caution is because we all know being an open source maintainer is an often thankless task. But it's absolutely something I think we should be raising. If you're using an enormous amount of Spring or Quarkus or something like that, I think it's absolutely reasonable to ask the people behind those frameworks what their carbon footprint story looks like. So, if you are looking to start improving your software sustainability, start with operations, not code. Aim to reach greater than or equal to 50% utilization for all the servers across your estate. Use light switch ops, turn off underutilized machines, that's to say zombies, and do manual right-sizing. Use auto-scaling if possible, including scaling back down again, not just scaling up. Run more applications on the same hardware, that's to do multi-tenancy. Obviously, I couldn't do that with my examples earlier on, but you absolutely can. Use more efficient CPUs that are matched with your workload requirements, and look at where your workloads run from an environmental perspective using tools like electricity maps and apply demand shifting and shaping if you've got that far in the process. Finally, if you or your organization are actually doing good work in this area, please share your experiences publicly. There is an absolute dearth of good information and good success stories. There are companies doing good work. For some reason, on the whole, we're not talking about it. As an industry, we make progress when we share knowledge. You can do that at conferences like this one. You can write a blog, you can write a video, you can get published on a website, whatever. But we need more information about this in the public domain. If you want to do that and aren't sure about how to go about it, that's absolutely 100% in my wheelhouse. I was chief editor at InfoQ for 6 years. I've been a freelance journalist for many, many years. So if you want help with that, do reach out to me. I'm very, very happy to help. But if you do one thing, share your knowledge, particularly in the green space. We really, really need it. If you want more on this, here are the books that I would recommend. So the one on the left there is my own one. It's free. It's available from the New Stack. I'd intended it to be like a really quick, easy on-ramp to this whole topic. So it's designed to be a book you can read in the morning. Okay? I'm quite happy with it. I've had nice feedback about it. From there, Building Green Software, the Ann Curry, Sarah Bergman, Sarah Sue book is excellent. It's probably kind of a definitive book on this subject at this point in time. I really enjoy Bill Gates' book, How to Avoid a Climate Disaster. Really recommend that one. And Hannah Ritchie's book, Not the End of the World, is wonderful. She is the data scientist at Our World in Data. Quite a lot of my graphs at the beginning of the talk came from her work. It's a fantastic book. It's quite optimistic. And I can't recommend it highly enough. So do read that one as well. With that, I am out of time. If you want a copy of my slides, scan the QR code. That will take you to slides and resources for this talk. I've been Charles Humble. Thank you very much indeed for listening.